So firstly, welcome and thank you everyone for joining us today. My name is Aaron Freed, working on the revenue operations team here at Kubecost. And today we're going to chat about Kubernetes cost optimization and how you can save 30% on your Kubernetes cloud spend. So just moving on quickly just to the agenda on the next slide. We're going to chat a little bit about Kubernetes cost monitoring and why you should care about it and why it's important. We'll go through 5 anti-patterns for overspending and with some actionable tips that you can start to deploy right after this call. We'll chat through the Kubecost framework for optimizing your Kubernetes cloud spend, and then show you a little bit more about some of the things we're working on here at Kubecost. If at any point you have any questions, just submit that through the Q&A, and we'll be able to get to those. And if we don't get to it during this presentation, we'll follow up via email. Perfect. And just onto the next slide, I'm very pleased and honored to be joined by 2 outstanding gentlemen. First is Webb Brown, co-founder of Stackwatch, the creators of Kubecost. Prior to founding Kubecost, Webb was a product manager at Google working on Kubernetes and cloud monitoring when it was known as Borg at the time. I think that's right, Webb, the predecessor to Kubernetes. And Webb is joined by Goodier, solution engineer here at Stackwatch as well. Jesse has been an excellent partner to a lot of our clients as we work through deploying Kubecost within their environments, and is also a certified Kubernetes administrator. So thank you again for everyone for joining today, and I'll hand it over to Webb to teach us how we can save some money.
Excellent. Thank you so much, Aaron. Really excited to be with you all today here. Plan is to give a bunch of practical solutions for how you can go and optimize spend with the goal of saving 30% or more. We're going to do lots of live demos. Like Aaron mentioned, drop questions in Q&A at any point, and we'll jump all over them. With that, let's dive in. So first, like quick context, which is Kubecost itself was created to help teams really monitor or understand and then optimize their Kubernetes spend. So like Aaron mentioned, our founding team previously worked on infrastructure monitoring at Google. We launched the Kubecost open source in early 2019. Everything we do at Kubecost is built on top of open source. That includes, Kubecost itself, the OpenCost project, which we were co-founders of, which is now a CNCF project, Prometheus, and a handful of others. Kubecost itself is self-deployed by default. It can be Helm installed in minutes. You don't have to share any data with anybody. It is all self-contained. We do have a hosted platform of a distribution of Kubecost that is in the works and will be coming soon. And we just announced a really exciting collaboration with the AWS EKS team, where you can now get more services for free, supported by Amazon with that new launch. So go check out EKS cost monitoring. And then some really quick metrics. We work with thousands and thousands of teams running Kubecost today. Estimated more than 5,000 currently run it across all major cloud providers, as well as on-prem platforms and even air-gapped environments. Kubecost itself is monitoring billions in spend, and Stackwatch, the company that originally created Kubecost, has more than $25 million in funding from a bunch of great investors. So let's talk about Kubernetes as a platform first. We feel very strongly and have seen it over and over again have the opportunity to greatly reduce cost compared to VMs or other deployment mechanisms. But it's a powerful and even complex platform, which can lead to overspending. So why is that the case? First is that teams that fully embrace Kubernetes and cloud native deployment typically have more decentralized deployment mechanisms. So moving more towards microservices where there's less of a centralized team controlling, governing, and really monitoring releases. As a result, releases tend to happen faster. You tend to have more dynamic environments where things are constantly changing. And then third is there's a bunch of new, very powerful abstractions with Kubernetes that are abstracted across cloud provider, where teams can do things like provision 1,000 GPUs with the click of a button or a single command. That is incredibly powerful. It also can be costly when you make a mistake if you don't have guardrails or governance in place to monitor that. So with that context, let's talk about where we are today as kind of an ecosystem, if you will, running Kubernetes. And I'll start with a really interesting survey from CNCF last year, which asked teams about the level of cost monitoring they have in place. And what you see is the majority of teams, approximately 2/3, do not have accurate visibility in place. And we just feel very strongly that this is the foundation, really the starting point to having efficient infrastructure and efficient applications in Kubernetes or cloud native environments. So the downstream effect of not having this cost monitoring in place, another pretty interesting study, and not just about cost, but about other areas. This Flexera State of the Cloud report from earlier this year shows that teams on average estimate that they have about 1/3 of their spend that is going to waste. Anecdotally, when working closely with hundreds of teams in the last couple of years, we believe that most teams start at even higher point of this than on Kubernetes environments when compared to kind of general cloud environments. But not to fret, there are solutions available. And so with that, we'll dive into how we start tackling like cost inefficiencies or waste. And if there's one thing you leave today with, I'd love for it to be this. And it is, at the end of the day, the starting point as well as the ending point is looking at the cost efficiency of your infrastructure. So what does cost efficiency actually mean? It is a utilization-based measurement of all the dollars you're spending in Kubernetes. So more specifically, of every dollar that you spend, what is actually going to, say, powering applications? So if you're looking at, say, CPU, what percentage is going to running applications versus sitting in idle state? If you're looking at memory, what amount of dollars spent on memory is going to just total idle memory versus actually powering something that is efficient or effective for your business? And so, of all the teams we work with, we've collected a lot of data that teams have shared, and in aggregate, we've seen that most teams start below the 20% cost efficiency threshold, but there's typically a quick path to 60% cost efficiency. So that means you are reducing waste by a lot, and ultimately that would lead to approximately a 65% savings in Kubernetes costs. So we see time and time again where teams are even able to overshoot this 30% savings target. So let's talk about how you actually do that. Again, we think that the foundation starts with accurate cost visibility as step one. So I'm going to jump to our first demo of the day. This is showing a UI in the community version of Kubecost, which you can helm install in minutes. And again, don't have to share any data. So a couple really important lessons when looking at cost monitoring. First is understanding and being consistent with how you are isolating or organizing tenants. So this could be using namespaces, this could be using labels, this could be using even microservices. What's important is that there's agreement across the organization on the standard and mechanism that you're going to use here. Again, whether it's any of these, annotation, you name it, it's really about consistency and having agreement across the organization. So from here, once you have correct isolation across tenants, what's really valuable is to be able to see trends over time and then also have the ability to drill in where you see an unexpected cost or want to learn more. In our case, this multi-cloud namespace is much more expensive than I would expect. So I have the ability to just one-click drill in and look at all the actual controllers in this environment. So deployments, stateful sets, daemon sets, jobs, etc. I'd see all of those, everything that's running in this namespace over the last 30 days, ranked by cost. Again, when we talk about the golden savings metric, I can see that cost efficiency metric for the entire namespace, as well as every individual deployment that's being run. So let's say, this Thanos store stands out to me. It's both costing more than I would expect, given the value it's delivering, and it also has, relatively low efficiency. So from here, I can go in and see that I've got 3 replicas running consistently. I have the ability to now drill into those individual replicas and better understand, the requests they're handling, the value that they're creating. So again, this is just the starting point for us to look at, both cost as well as efficiency across all of these, like whether it's applications, teams, departments, et cetera, all of these like logical units that map back to your organization. Okay, so again, we view that as the foundation or the starting point to great, cost optimization. So we touched on a goal of isolating tenants in a way that map back to the value that they're creating for your company. Again, this ability to see trends over time as well as drill in will help you just clearly spot, obvious issues, given that the context of things being run in your organization. And then lastly is, as you scale up the number of clusters, providers, et cetera, it can be really valuable to have a single view of all of these environments in one place. So there you can look at costs across dev prod staging or costs across, providers, teams, et cetera, that may not actually be in the same cluster. All right, great. So now that we have accurate cost visibility in place, we can start talking about using that foundation to identify and remedy 5 really common anti-patterns that often lead to overspending. And I would say that we see multiple of these anti-patterns in 90+% of the scenarios when we start working with teams. So oftentimes big opportunity for optimization improvements. So optimization opportunity or anti-pattern number 1 is this notion of orphan resources. So these are cloud resources that are externally provisioned that do not currently have an active owner, and therefore it is near impossible for them to actually be delivering value because they're actually not connected to any sort of application. So common examples would be persistent volumes, like external IPs, load balancers, et cetera. One common example would be that during application teardown, these resources didn't get cleaned up. For a while, there was actually a Helm bug where persistent volumes weren't being actually deleted, even though in the state of Kubernetes, the Kubernetes object was removed, the underlying or backing disk was not removed. So let's take a quick look at a demo at how you would identify these. So first, we're going to look at, again, the community version of Kubecost. This, again, is totally free, can be installed in your cluster, but we'll also talk about the actual methodology that's being used here in case you wanted to build something on your own or use another solution. So this is a view of my cluster that is then connected to my cloud provider. So I've done a cloud integration in the free version of Kubecost to now see that these external resources are provisioned and don't actually have an owner. So here's an example of a disk that would have been provisioned, for within the default namespace, but that tenant is no longer connected to that actual disk. So what this is actually doing is going and looking at cloud provider APIs and then mapping it back to Kubernetes to see if there's any alignment between those two. And again, if there's not actually a connection or an owner, then it is deemed as orphan. I would say that some of the time that this is done intentionally, as in you're parking a disk or parking a load balance and you're dynamically going to connect with it. But 90+% of the time, these are opportunities to go and clean up resources. So we jump back to our slides here. This commonly leads to, especially as you scale, around 5% of an opportunity to optimize spend. Sometimes it gets up to 10%, but that is typically when you have many engineering teams, or like many different departments with kind of no process in place for managing this. While it's like a smaller win, the upside here is it's typically a quick process. Teams can go and review this and identify opportunities to save really quickly. So how do you do this really effectively over time? You really want some mechanism to where when this becomes a big enough problem, you go and take action. That could be, setting an alerting rule. That could be having a dashboard that you could monitor. That could also be having a management platform where these insights, whether Kubecost APIs or cloud provider APIs directly, are made available when you're actually managing the state of your infrastructure. And then part two of this, which is kind of pro tip, to the extent that you can identify an owner of these resources, it can make it really easy for you to then take action. And what is common here is send some type of alert to the owner and just say, if this isn't claimed within, say, 7 days, it's going to be removed automatically. So that is insight or anti-pattern number one. Let's jump to number two, which is actually pretty similar. It's kind of the Kubernetes in cluster mirror of insight number one. So this is identifying Kubernetes workloads that are not providing clear business value. So common examples would be deployments or staple sets that were in use but are now deprecated, but are actually still deployed and consuming like real resources. This could also be workloads that only get usage on, say, weekdays during business hours that get run overnight or over the weekend. Again, this tends to happen more and more as you scale as a company, whether that's growing the number of engineers, building applications, or the number of teams working on common shared infrastructure. Because again, it just gets hard to really understand who the owner of things are, as well as how they're actually being used. So let's jump to our next demo. And what we will see is the Kubecost heuristic for identifying these. So in particular, Kubecost would use a collection of network, egress and ingress, as well as compute usage, with the general thinking that anything that is low consumption on all of these dimensions is unlikely to be doing meaningful work, right? If it's not clearly doing any sort of computation and it's also not talking on the network, it's probably a pretty good sign it's not adding a ton of value. But this is one case where definitely you want to apply some sort of business understanding of the underlying application. So again, this would be a view of kind of like dollar ranked opportunity for a win. We can really look at different thresholds. If we want to go all the way down, to a really low threshold and look for opportunities, we would then see, things that we could go and clean up or remove. And this could be, removing deployments entirely. It could be reducing the number of replicas of deployments. It could even be removing an entire namespace, for example. Again, I would say as teams scale here, it's really valuable to have a single pane of glass as opposed to jumping across from cluster to cluster once you get into dozens and dozens of clusters. So how this is implemented is this is actually using underlying Prometheus time series data to do these calculations. So Kubecost itself builds a bunch of caching layers, so you can do this over long time periods like 30 days and have it still be really quick at scale. But you can go capture these underlying metrics in Prometheus to look for low network traffic, et cetera, yourself directly. All right, cool. Let's jump back to our slides. So this is another example that's on the order of magnitude of 5 to 10% like spend reductions. Again, as you scale as an organization, this tends to grow. I would say it is still in the easy category, but a little bit harder than like orphaned external resources, just because this is a scenario where you tend to need to apply some sort of organizational or business knowledge to understand if something is actually an owner here. Again, having a mechanism for when this crosses a certain dollar threshold can be really valuable. So you don't have to feel like you constantly review this. You can just be alerted or ping the actual owner itself when this, again, becomes a meaningful percentage of your overall spend. All right, jumping to insight or anti-pattern number 3. This is, I would say, a less common one, but when it happens, it can be really expensive. So we call this rogue deployments or just workloads gone awry or gone crazy. So examples here, we have seen many of them. This could be, just accidental misconfigurations. So, accidentally asking for 100 or 1,000 replicas when really looking for 10. Application bugs that actually drive auto scaling, whether it's a misconfiguration in the autoscaler itself or at the application layer. And if you can believe it, we have now seen multiple Bitcoin miners detected by Kubecost today. So again, these are less common, but having this monitoring in place is the foundation for catching these, right? And oftentimes when you do catch them, they are bigger. So like, 10 or even higher percent. This can be a little harder just because it does require kind of ongoing monitoring as well as business knowledge to catch these. So Kubecost has the ability to alert on either sharp, unexpected increases in spend or spend anomalies. It can also do things like set budgets at different levels, whether it's namespace, label, or annotation, to where these individual owners of that part of your infrastructure can be alerted. So I think kind of 2 patterns here, which is either as an infrastructure owner itself, you get alerted when, say, the cost of your cluster or even the cost of any namespace increases by, say, 100% day over day, or you give, budgets or anomaly detection permissions to the individual tenants, whether it's application engineering teams or anything else in your actual infrastructure. And again, ultimately here, you're looking to just put some sort of guardrails in place to prevent having major damage. Again, we've seen these costs into probably the hundreds of thousands of dollars now, in a relatively compressed period of time, like less than a day or over a weekend. All right, so now jumping into where we see the opportunity for really big gains. And this is looking at this notion of over provisioning, where specifically excess capacity is provision for like well above and beyond what application needs actually are. And again, we talked about it a little bit earlier, but the net effect of this is, most teams run with anywhere from 60 to 80%, if not higher, idle capacity in their cluster. This will be the guiding metric to determine if we've done this successfully or not. So when we talk about doing successfully, I want to jump over to a two-part demo, actually. And it's really important to think about this order in this situation. So first, we want to think about optimizing or right-sizing the applications. Then once we've done that, we can right-size the underlying infrastructure. So both parts are required to ultimately reduce your Kubernetes spend, right? Because it's the underlying infrastructure changes that ultimately matter. But let's start with the application level, because again, you have to better fit resource request for the Kubernetes scheduler before you get to actually right-sizing the underlying infrastructure. So by doing this, we're actually looking at tuning Kubernetes request in proportion to the actual SLA or resource requirements of the application itself. And so this actually depends on the context that you're currently looking at. So you're going to want to provision for an HA application pretty differently than you're going to want to provision for a dev application, for example. And the reason for that is you're probably okay with a dev environment being CPU throttled, for example, 1% of the time or maybe 5% of the time. Whereas an HA application, you're willing to provision more resources to really go out of your way to have, say, 5 nines of uptime / non-throttled time. So this context really matters when we're looking at workloads. But once we have that context set, we can come in and look at different opportunities. And again, the actual dollar like savings resulted from them. So in this case, like with this workload, we see in just a quick example that it's actually using 0.4 milli CPUs. So very little like CPU usage, but it's actually requesting like more than 100 times that. So given the context that's set, this like Kubecost would be providing a recommendation of reducing CPU requests by 10x, and therefore having like a meaningful savings impact. On the other hand, when we look at RAM requests, this workload has like some amount of RAM usage, which is to be expected, but it actually has 0 requests associated with it. So this workload, when there's resource constraints on the node that it's running, or nodes, if there's multiple replicas, would actually be at risk of eviction. So it would have a performance like risk unless you set a recommended request. So from here, we can actually drill deeper. We can look at individual pods. When deployed, Kubecost can like directly link to your Grafana dashboards. So you can look at this in a ton of granular detail at an individual pod or like, replica level, so that you are, again, have really high confidence when you're setting this, because not only can this have meaningful cost impact, it can also touch on performance and reliability. All right, so now that we've gone through and optimize this like infrastructure, or sorry, these applications, we can start to then think about the underlying infrastructure. And that takes form in essentially like going through these bin packing exercises, which is, given all of the right size applications we are running, what is the most effective and efficient combination of nodes that are available from my cloud provider? And Kubecost provides this in 2 different formats, what we call simple and complex, where simple is you have a single type of node pool. So it's your instance types are totally homogeneous across your entire cluster. Complex is where you could have multiple node pools, depending on, again, the resource requirements of your individual application. So again, going through this application to infrastructure exercise, it is not uncommon for this to have massive, massive savings. And the reason for this is, again, kind of starting with that foundational view, which is most teams don't have visibility in place. And so when you don't have visibility, it's just really common to say, I'll just drastically over provision, because the last thing I want is to like unnecessarily risk, say, CPU throttling or, ohm eviction. So this is a major opportunity. This is oftentimes done with just a manual review. Kubecost itself can then automate this right sizing piece, but then teams can also do things like integrate it with their CI/CD pipeline, for example. So Spinnaker and a couple other integrations, we can use these insights or recommendations at the time of deployment to right size those applications, and then again have the ability to right size the underlying infrastructure. All right, let's jump back to our slides. So jumping to our last anti-pattern or optimization opportunity is this notion of teams using mostly on-demand like instances at full price. So we see it as really common where teams will select a static like compute type or pay schedule, and then stick with it, whereas the application needs actually tend to drift over time in most dynamic Kubernetes environments. And so you present yourself with more and more opportunity as time goes on in most scenarios where you can, again, tweak this underlying infrastructure. So, just to like set the stage here, teams are mostly choosing between on-demand, reserved instances, or savings plans, or spot or preemptible nodes. Depending on your application and how it can be replicated, and also the SLAs or kind of uptime requirements, one of these may be better than others. It can also be deeply tied into how predictable your business is and how well you can forecast kind of resource demands 1 year out or even 3 years out when you're thinking about longer term, like reserved instances or savings plans commitments. So this can be, in the medium to hard category, depending on, those dynamics, but the opportunity for savings is absolutely huge for most teams. The reason that this is hardest is you want to do this without any impact to reliability. And specifically with spot and preemptible, there's a lot of Kubernetes complexity that you really want to think through, things like replication and pod disruption budgets and potentially taints and tolerations and affinities. We'll save that for another topic where another session where we can go really, really deep. But again, the upside is really big here. I'll just talk about the environments that we see or the patterns that we see when this works really well. Here is one where you have this predictable baseline of compute needs over time, and you are reserving these or using savings plans to reduce your spend from 30 to 70%, depending on your visibility, and then using on-demand workloads that actually auto scale, dynamically in proportion to the load of your actual application. So again, when we see this implemented, this can be super powerful, and it alone can have a 50+% like savings impact. Again, you want to be really thoughtful when tuning auto scaling and making these what are ultimately financial commitments to your cloud provider. And then pattern 2, which is actually pretty similar, which is again this base load you can reserve, and it gives you some amount of stability in the underlying on-demand infrastructure, whereas then you use spot to actually burst with load or application demand. This again requires you to kind of architect or select applications that are on these burstable spot nodes to be resilient to failure. Again, Kubernetes itself is built to do this really well, but there's some complexity that you really want to think through before you go down that path. All right. So if we just recap and say, these 5 anti-patterns, if you can proactively avoid them, again, we see an opportunity to reduce spend by 70% or even more, which is, well above our goal of 30%. But that, the vast majority of teams can reduce spend by at least 30%. In the process, by doing things like removing, orphaned workloads or, catching Bitcoin miners, you can, reduce security, concerns in the process. And ultimately, it's not actually just about the savings themselves. We as engineers want to make it to where your time is as efficient as possible to actually realizing these savings. So, definitely as you pursue these, like, think about your own time. And again, that's where we talk about these like dollar thresholds for some of these insights. Sometimes if it's, only going to save you $100 or $500 a month, that's not worth the exercise of your organization to go and, clean that process up, for example. So really think about, again, the time commitment that's going to be required on your end. And Kubecost itself was built with a goal to try to help, really save time for teams. So if you do have any questions about this or any more, please reach out to us at team at Kubecost, and we'd be happy to share more. Again, just provide guidance or help you with our free or community version or otherwise. So then I want to talk about just one last framework to give you before I hand it over to Jesse. And this is really around when we think about optimizing infrastructure at Kubecost, from our years of working with Kubernetes, as well as our experience at Google, we think about every change you're going to make is going to influence one or more of these 2 variables. So one is the amount of time compute resources are provisioned, the amount of resources that are provisioned, as well as the price of those resources. And so this is meant to be just a general framework to think about everything you're doing, whether it's disk or compute or GPUs. Ideally, you want to get to kind of as close to just-in-time provisioning and then spinning resources down as soon as you're done with them, and then also provisioning just the right amount relative to your ability to forecast resource needs and the SLAs of those applications. And then lastly, again, we want to be targeting the most cost affordable resource class, whether that's spot or glacier storage or whatever it is for that particular resource that meets your needs and SLAs of applications that are built on top of them. So again, that is how we think about optimization from just a very general sense. And we found that when teams kind of adopt this, it can lead them to the path of tons of optimizations. This is just meant to be a quick kind of grab bag. We'll share this video after. These are kind of all of the insights that are available in Kubecost. I believe there's, 13 of them here now. And again, these are touching on different components of this, whether it's the time something is provisioned or deprovisioned, the amount of the resource that's provisioned, or the price of a single unit of that particular resource. So with that, I can hand it over to my partner, Jesse, to tell you a little bit more about next steps and about Kubecost itself.
Thank you, Webb. And I will share my screen. Actually going to address a couple of questions that came up more than once on how Kubecost works, and maybe dive into a little bit more of a demo to maybe help with those questions. So the first one was, how does Kubecost get its metrics? And we are using built-in or tools that are very common in most clusters today. They are, the Kubernetes API, Kube State Metrics, Container Advisor, which the screen I'm showing you right now, you can see that we're storing the data in Prometheus, and Prometheus is also scraping Kubecost. in order to understand the cost data during those time windows. And so primary question I get a lot is, I already run Prometheus and I have Node Exporter running on my cluster already. Do I really need to use the Kubecost provided? The answer is no, you do not need to use the provided utilities. And network metrics is Kubecost specific. I'll talk about that in a second. But we have easy ways to disable Node Exporter, and Kube State Metrics is going to be disabled by default in a future version. The thing I would say that for when you're using Kubecost free in a single cluster, using your own Prometheus database is very straightforward. You tell us where that Prometheus database is, and you provide a scrape config. And I'm not going to get too technical. I was told that earlier, but it's straightforward. All right. Network metrics, I think, is best done in a demo. So one of the cloud costs that Kubecost does measure is egress data, and this isn't enabled by default in a typical deployment. And the reason for that is it's an additional daemon set that runs in your cluster, and a daemon set is a pod that runs on every node, and this particular daemon set needs write access to the node in order to enable network accounting on that node. There's additional overhead to that, but the overhead is so light in comparison to many customers' egress costs that this is generally worth enabling. And so you can see in the cost allocation view this network column, and that is purely egress cost. And Kubecost understands whether it's cross-zone, internet bound, cross region. One cool way you can use this to save costs is we see cloud misconfigurations where you've got a tool running in US East 2 and then a S3 bucket in US East 1. And that incurs egress cost. And if you were to co-locate the S3 bucket with the Kubernetes service that's consuming the resources, you could potentially save an incredible amount of cost. Now, obviously, this isn't going to apply to 100% of workloads. There's reasons why you'd have separate geographies like that. But many times there's misconfigurations or at least opportunities to tune what's going on. Okay, next question that came up, a little bit more on architecture. Kubecost in the short term uses the cloud APIs to find on-demand prices for the nodes that the containers are running on, the cost of storage that the storage class is consuming, and the egress data for that particular region. And in many of our customers and users of large size, they've got significant discounts with the cloud provider. Kubecost can import those cost and usage reports in order to reconcile the estimates that have been done in the short term with actual bills. And that is a one-time setup, per cloud provider or per account for those cloud providers, where you give us read-only access to pull in that data. But that is very commonly used for many Kubecost users. In a multi-cluster environment, there's a couple questions on that. So Kubecost does support multiple clusters and a single pane of glass user interface. In the case of, we've got customers with thousands of clusters running all over the world and tens of thousands of nodes. Only the primary Kubecost cluster needs access to the billing. So the Kubecost primary cluster, you can think of all secondary clusters as every cluster that we're monitoring out there. It doesn't need a Kubecost UI. It doesn't need the caching that Kubecost UI does in order to provide fast reports. And so we basically just have a metrics exporter sitting on the secondary clusters that are storing their data in a central S3 compatible bucket. And we use Thanos to accomplish that. Right. And so the primary Kubecost cluster is doing some more heavy lifting One being pulling in the cloud and usage reports, which in many users, it's millions of lines that we're ingesting in order to find those specific nodes, and then doing that reconciliation. So we very commonly see Kubecost using a significant amount of resources on the cluster, but we're very transparent about what we're using. Just to jump into a demo environment, you can see Kubecost running on this cluster. Actually, excuse me, I'll show you. This is a 3-cluster environment. And so we're aggregating all the Kubecost namespaces and all the clusters that are connected in this environment, and showing the cost of that namespace inside of this UI. So you can see in total, over the past 14 days in this case, Kubecost is consuming $92 of Kubernetes resources. And maybe that's significant, maybe it's not, but at least we have visibility into what is driving costs in these clusters. More on the allocation, which is really cool, and I will use the Kubecost namespace for this example. So how does Kubecost understand the actual cost of these workloads? And that is doing this drill down that Webb described at the beginning of the call. And that when I click on a namespace, I now see the controllers that make up the resources in that namespace. A controller, typically like a daemon set or a deployment. In this case, I'm going to click on a deployment. And then I see all the pods that are part of that deployment. At this point, if I click on one, I then see the containers. The containers are actually what is consuming the resources on the node. And the container has both what Webb said, usage with the CPU and memory that they're using, as well as the reservations, which Kubernetes calls a request. And so when Kubecost does that cost determination, it is based on the max of either usage or request, right? So if you have a request for 4 gig of memory, but you're only using 1 gig, no one else could use those other 3 gigs. So it does cost that workload that much money. And so we know that this container is running on this particular node. I can see that it's a AWS node. And if I were to click on it, it will then bring up a screen showing how much this particular node, which is an M5 extra large, costs per hour. Further to that, how much the marginal cost of the CPU memory is that this particular container is using. And so Kubecost knows which node, which that container is using, and how much resources it was consuming on that node during all these periods of time. And so that when I go and I look at a history of, in this case, the namespace is running in this demo environment, how much resources they use for those nodes during those times. And so if they were scheduled on really expensive ones for a few days and then they got moved to cheaper nodes, you would see those costs reflected inside of these historical graphs. All right. I really appreciate all the questions that came up. It was hard to keep up with all of them. If there's something that I'm missing right now, please let me know. In the meantime, we'll get back to the slides. Okay, alerts and governance. And this did come up. We at Kubecost call scheduled reports alerts. And I realize that we probably could easily adjust the UI to make that obvious. So I apologize. Inside of alerts is this create alert button on the bottom right. This is where we can say, I want a recurring update. So every 7 days, the owner of the application one namespace gets the reports telling them how much that cost. So just every Monday morning, they get that in their inbox. Or we also support Slack webhooks. And I don't run Teams, but I have customers that do, and they say that Teams works fine as well. So any webhook should work. And other reports that you can see here, I'm not going to go through them all, but another one would be, you've got an anomaly going on. That namespace, has grown in costs by 30% over the past 7 days. Let's send a message to that team, let them know maybe this is expected or not, but you can look into it. Okay. all of these reports, as well as the scheduled reports, as well as just views into the Kubecost dashboards, can be created dynamically in code. And so if you want to deploy Kubecost through Argo CD or whatever CI/CD tool you're using, these can all be templated out and then deployed as code. We're working on making that a little bit easier, but it is already supported today. Another enhancement, but I won't speak to when it's going to get implemented. Maybe Webb knows more detail, but one thing on scheduled reports that we're working on, kind of roadmap here, is the ability to send prettier reports. And so it'd be nice if we could make a PDF of this Kubecost namespace details here, and then send that so that this user does not need to log into Kubecost in order to understand what's going on with the costs of their application. Another really cool feature we have is the ability to aggregate by a label. So the best label would be cost center, right? And so if you're doing chargeback and everyone's got their cost center label that they always deploy with their applications, regardless of it running in a specific namespace, we can do that. And so like app is a particular, common label that, is in Kubernetes. I'll just use this as an example. Let's just assume that this was my cost center. And now I can see the list of all my cost centers and understand what they were for the past month, right? So another time window we'll look at here is last month, right? So there you go. Create a PDF of this, send it to the CIO, and now they've got cost transparency as to who's consuming what in all the clusters running in the environment. I will wrap it up there. If there's more questions, I'm happy to answer them. I think we have a final slide here on the ecosystem. Kubecost is open source. We get contributions. A couple of them been like helping us support Scaleway or Alibaba Cloud. So really appreciate that community, getting better cost visibility into the various providers out there. We already support custom pricing for providers that don't have APIs built into Kubecost today. And so anything works. It's Kubernetes. Just a matter of how close we can get to the accurate cost data.
Thank you, everyone, for joining. Really appreciate all the great questions. If you'd like a personalized demo or want Jesse or a member of his team to walk through your environment and see all of your live metrics in a Kubecost environment, we're happy to do so. So feel free to just drop us a note on www.kubecost.com/contact or send us an email to team@kubecost.com. I'll post that in the chat right now. And we'll send out a recording of this if you want to share it with any of your colleagues. And thank you again for joining. It's been an honor, and thank you, Webb and Jesse.